Hi, my name is Ernie. I'm a research assistant in Academia Sinica, Taiwan. Today I'm going to talk about our work, MeDM. Our method leverages pre-trained image diffusion models for video-to-video translation, without any fine-tuning and test-time training. With the advancements of text-to-image models and open-source models like Stable Diffusion, image generation have become easier than ever. And lots of researchers have extended original text-to-image models into something even practical and powerful. And this work makes the diffusion models conditioned on some low-level or structural inputs like strokes, edge maps, and segmentation maps. And these ingredients are easier for us to produce, and we can use a powerful stable diffusion like an image-to-image translator. This enables a wide range of applications. A very natural question to ask is that whether this method can work on videos if we just simply apply them to each video frame independently. Like for example, I want to give this Asian girl blonde hair and blue eyes, and then make some simple motion like just move the entire image from right to left. Can it work? Alright, so unfortunately, there's no free lunch here. Let's see what we need to move from image-to-image translation to video-to-video one. We can of course train the video diffusion model if we have data. After our video, just like images, they are just digital signals and we can model them in the same way. However, training a video model is like a GPU monster, but it shouldn't be because there's actually a lot of redundant information in videos, and we should make an inherent knowledge from existing image models like Stable Diffusion. And there are of course many other approaches to this problem. However, let's just jump into our method. We think video are essentially image plus motion. For image, we already have those amazing works in previous slides, but for motion, we're talking about very detailed motions like pixel level motions. And since we are dealing with translations, we can easily derive the motion from the input video using optical flow estimator. An important character for our method is that it requires no fine-tuning, no test-time training, no nothing, and it only takes around triple the time it needs to generate this frame independently using Stable Diffusion, specifically for 6.8 seconds per frame. And let's take a sneak peek into how MeDM can boost the existing model performance. Pretty great, right? So to put it into perspective, let's extract vertical beams from each video frames and stack them horizontally to get the idea. We can see that video generated by our method reconstructs stripe-free images, which means the temporal coherence is good, and on the other hand, without our method, the reconstruction is terrible even on this simple toy example with artificial flows. Before jumping into our method, let's rethink what is a video. In our perspective, we think video pixels are essentially views to the underlying object, that is hands in green boxes and a dragon baby in the orange boxes here. And even though this object may not physically exist, what's important is the physical fact that the color of these points on the object surface should not change drastically through time. So we expect three essential properties for a data structure that can enforce such physical constraints. The first is a global pixel repository that representing the entire underlying world, and the fast and efficient conversion between a repository and the original videos, which is actually finding the correspondence of pixels between both data structure. And the final one is a method to mediate between pixel values in the videos when the temporal coherence is bad. Let's talk about these three properties in detail. The repository is a 1D tensor, and it stores the necessary pixels to construct all objects and backgrounds in the video. It should not be difficult to find that the number of pixels in the repository will definitely be a lot lower than what it is in the original video. This is because of the information redundancy we talked earlier. For example, like these hands in the green boxes, they are all associated with this range of pixels in green here. And likewise for the dragon baby, so this repository ensures that all corresponding pixels share the same values. And for the correspondence, which allows for the conversion between repository and the original video, we want an efficient way to retrieve these pixel values from the repository and rearrange them into video frames. We also want to use these video frames to update to the repository, so we use an encoding called flow coding, which uses the index to the pixel repository as the encoding values. So we know which group of pixel belongs to specific frames. Concretely, here we fill the first encoded frame with 0 to 4, and with the optical flow of the first frame, we can see all pixels are moving to the right. So the first column should be propagated to here in the second frame, and the first column of the second frames are new, which means it does not exist before. So we fill it with new index 4 and 5. Likewise, using the octal flow of second frames, where all pixel stays in its own grids, we propagate the codes as is to the third encoded frames. Finally, there's the mediation. We have looked how words the direct outputs of the baseline method were, so given these massive video pixels, we are going to use our data structure to harmonize these video frames, or we can say conducting a mediation between them. For the highlighted pixel of the index 2, for example, we have 3 different pixel values here from the 3 video frames. We have to find the value that they can agree on, so we find the simple average among them is good enough and really fast. The mediated results will be saved to the corresponding location in the pixel repository. And finally, the common value is assigned back to all associated locations in the video. You may ask why bother making a repository where its only job is copying the value back and forth. It is because it makes our method super easy to implement and run really fast. And let me show you this PyTorch snippet that is actually used in our program. We just simply put the video pixel value xt into repository according to the encoded video xe. We also keep track of the count so we know how many pixels contributes to each location in the repository and calculates the average accordingly. Since we average these pixels, we have to make sure this operation is meaningful. As suggested by DDPM, when blending the noise version of this image, we are actually doing a semantic interpolation. So we follow multi-diffuser and run over mediation every time the noise image has been predicted by the diffusion models unit. This is also a reason why our data structure must have a fast conversion and use the repository index as encodings. Because the operation runs in each denoting step, MeDM gradually pull the divergent pixel value closer and finally get a clean and temporal consistent videos. Alright, I don't know if anyone noticed, but there's a temporal correspondence guidance within our title, but we haven't covered it yet. So what is this guidance about? It's just simply using the idea of classifier-free guidance and suggesting we don't have to use a fully harmonized video in each step of denoising. The temporal consistency saturates with respect to human eyes. Although the modified prediction proved the temporal coherence, but it may come with slightly worse image quality in comparison to the original prediction. So the weight W is kind of like a trade-off for user to choose between better temporal quality or better spatial quality. And we conduct a quantitative experiment that uses an estimator on the generated videos to get their optical flows. And compared to the ground truth, we can see with the strong guidance, the optical flow errors are lower, and which suggests the video is smoother. However, a significant problem when using our method with latent diffusion models like Stable Diffusion is that these diffusion models work first use an autoencoder to compress the sample into a low-dimensional latent space and perform diffusion and denoising in the space. Since our method performs coding in pixel space in the original dimension, we need to cast the noisy sample from the latent space to the pixel space. Fortunately, we can see here that the autoencoder only works on Z0 and it cannot cast the noisy sample back and forth successfully when the sample is ZT, when t is greater than 0. Our workaround is to use existing diffusion formulation to first derive a clean sample x0 from the current noisy sample xt. This clean sample is far from the final outputs, but it has entered the distribution that the autoencoder is trained on. We'll see a concrete visualization later. And when we can faithfully cast the sample to a pixel space, MeDM takes control and does its jobs. And after the harmonized samples, we cast back into the latent space and we deriving the harmonized noise samples and perform interpolation with the original noise sample according to the guidance scale. Here's a visualization of the derived X0. To verify it can be processed by the autoencoder. We decode it, encode it, and decode it again, and obtain the image at each noise steps you are looking at right now. So here is our final result, and we showed it qualitatively and quantitatively that our methods outperforms all the baseline methods. And our method can also utilize for video rendering because it is a kind of video to video translations, and our experience shows that our method is best in class. Finally, here's an interesting application of our method. We can directly use it in video anonymization. Due to high sensitivity of human eyes to facial images, when we add noise to the video to a certain level and denoise it back using diffusion models, we can see the facial identity are completely changed, but the background and motion stay the same. With text prompts, we can also perform targeted identities editing if the name of a person like Einstein can be recognized by the text-to-image diffusion models. Thanks for your attention, and please check our project page MeDM2023.github.io for more video results. Thank you.